Today's warm-up question, it is going to look really familiar whenever you do your assignment today, because you're going to see a graph that looks pretty similar to this, and you're going to see again on your test. So I would very strongly encourage you to copy it down so that you have it to refer back to as you're working through the problem set today and preparing for your test. Which again, your test is on Friday of this week. Tomorrow you have a quiz, and then we'll go over it the next day, and then you have a test on Friday. Today's warm-up question says, Mr. Quigley is done showing off his mad skateboarding skills when he coasts to a stop from 1.2 seconds through 3.4 seconds as shown in the graph. Find his acceleration during that time and find his stopping distance. So most of the time whenever I've been giving you calculation problems, you have been given calculation problems with all of the information just in the text of the question. This is a little different because instead of putting it in the text of the question, a lot of your given information is in this graph. Okay, and so we're still going to label our given information. What we can see in the question are times. We can also see them in the graph. The portion of this graph where the acceleration is occurring is just this red or maroon section where there's a curve. Initially, he has some amount of constant velocity, and then at the end, he is not moving, and we can see that as well. But the time during which he is accelerating is just this segment, which is 2.2 seconds long. Again, I got that value because they gave me the numbers in the question, and I subtracted them. From 1.2 to 3.4 seconds is a duration, a time of 2.2 seconds. So that's the time of his acceleration. I don't want the whole time of the graph. I only want the time when he's accelerating because I'm using a calculation where I'm doing time of that acceleration. Okay, so that's the only number that's written in the question, but it's not the only thing that I know. Okay, the other things I can see whenever I look at this graph, I can see what my initial velocity, final velocity is. I can also see my initial velocity. But my final velocity in this graph is 0. That one's easier, so I'll start with that. And I know that it's 0 because it says he slows to a stop in the question, so I know that just based on that alone. But when I look at the graph, I can see that the slope of that green line at the end is 0. And so I know that his final velocity is 0 from that as well. Okay, I also can get an initial velocity from this graph, but it's not as straightforward. If I want to get that initial velocity, I have to find the slope of that green line because he's moving at some constant velocity as he enters that red portion of the graph. And so he has an initial velocity before that acceleration occurs. And that initial velocity is the slope of this green line. So you do that change in y over change in x, or rise over run. Because it goes through the origin, it's a little easier. So rise from this origin, point at the origin, 15. And then run, or my change in y is 1.2. So I have 15 minus 0 over 1.2 minus 0. I didn't worry with the zeros. But if I divide those two, 15 divided by 1.2, I get an initial velocity of 12.5 meters per second. I forgot to type my units, but it is positive 12.5 meters per second, and that's my initial velocity. And so that's information that I see in there. I'm trying to find acceleration, and that's definitely not something I can see. I see that it's happening, but I can't see what it is. And I'm trying to also find my stopping distance. Now, I will say this. It is possible for me to get a stopping distance by looking at this graph because it shows positions. I can look at the fact that he starts stopping. His position when he begins his slowing down is 15 meters. And I can see that up here it's somewhere between 25 and 30, but I can't see exactly where. If I could get more clear readings from the graph, I would actually be able to label his displacement from the graph alone. But because I can't tell exactly where that number is at, we're going to go ahead and calculate it instead. Okay, so we have two different things we're solving for because there are two different questions here. We're going to be solving for his stopping distance, which means we're going to be finding his displacement, and we're also going to be solving for his acceleration. And so with that, we can take a look at our equations. Acceleration, I can use equation A, VF equals VI plus A times T, because I know T, VF, and VI. For displacement, once I find acceleration, my options for solving for displacement are pretty much anything up here except for A. since it doesn't have it in there. So I could use B or C or D, but I'm going to go ahead and use equation C for my displacement because it's already set equal to it. You could have used D, it was also already set equal to it. That would have worked too. There's not one way to do this. There's 3 different ways you could go about this. All right, so I've got 2 different equations. I'm going to solve for acceleration first because it asks for it first in the question and because I need it to use the equation I chose. So acceleration substitution into that equation looks like this. VF is 0. It's equal to VI, which is 12.5, plus A times 2.2. Just as a quick reminder, because some of you are still making silly math mistakes with your solving, you cannot add 12.5 plus 2.2a. Okay, do not do that. It is not 14.7a. Okay, they're not like terms, don't do that. Instead, we're going to subtract 12.5 from both sides, giving me 0 minus 12.5 equals 2.2a, or negative 12.5 equals 2.2a. From here, you can isolate your variable, get a by itself, and you need to do that by dividing both sides by 2.2, and that's what you would type in your calculator. Negative 12.5 divided by 2.2 is going to give you an acceleration of negative 5.682 meters per second per second. So that is your acceleration, negative 5.682 meters per second squared, or meters per second per second. Okay, so pretty straightforward. We got a lot of information from our graph. Okay, now we can solve the second part of this. What is the stopping distance? And now I have an acceleration that I can use, so I went ahead and labeled it up here. And so we're going to plug into this equation that we chose earlier. Delta x equals VIT plus 1/2 AT squared, and when I substitute in, it looks like this. Delta x equals 12.5 times 2.2 plus 1/2 times negative 5.682 times 2.2 squared. And from here, when you solve, you're just doing the algebra. Okay, 12.5 times 2.2 is 27.5. Half of negative 5.682 is negative 2.841. And then we need to square 2.2, which is 4.84. We can then, again, follow order of operations. We need to multiply those together first and then add to this number. And when you do that, you get 27.5 plus negative 13.75. And when you add, you're really subtracting. Your answer ends up being positive 13.75 meters. And so that is his stopping distance. And again, that makes sense because we were from 15 to almost 30, and that would be almost 15 more, but not quite. And so that makes sense as an answer. But we couldn't see that number on our graph. Okay, questions about the warm-up. By the way, you do not have to type the plus sign, I don't think, in front of your answer. If it lets you, I guess you can. But make sure that you submit your answers in the assignment, the Google form. Okay, so again, you will see this again. I'm telling you right now, you have a graph that's kind of similar to this that you're going to see on the assignment today, and you'll see one like it on the test as well. All right, so let's get into the notes. And as I said, it's not really notes so much as some practice problems. This one says a stone is thrown downward at 5.2 meters per second into a deep well and is heard to hit the water 2.41 seconds after being thrown. Determine the depth of the well. I would recommend drawing a picture first just so you can get a visualization of what's happening in that scenario. So you can see that I have my stone that is moving downward. Thank you. At negative 5.2 meters per second. I did call it a negative number because it is down. And so I'm going to go ahead and label anything that is moving downward as a negative value. The time is 2.41 seconds. So not only do I want to label these in my picture, let's go ahead and label them as givens. I have an initial velocity of negative 5.2 meters per second and a time of 2.41 seconds. Those are the only numbers that I see in the question. However, what else do I know to be true about this stone? There's definitely something else that I have to label. Yeah, it's accelerating due to gravity. Okay, it doesn't matter if I throw it down or drop it or even throw it upward, which we're going to look at in a second. It doesn't matter what happens initially whenever I release it or throw it. The acceleration, once it's out of my hand, same number. Okay, it doesn't matter, it's in free fall. Its acceleration will be negative 9.8 meters per second squared. And it's negative because it's downward. Okay, so those are the pieces of information that I need to use, or my givens, in order to solve for my unknown. My unknown is the depth of the well, which means I need to figure out what the displacement of the rock is, because that will tell me how deep the well is. And so I have my givens and my unknown, and so we're going to take a look at these equations again. Which of these equations, A, B, C, or D, can I use to solve for delta x when I know VI, T, and A? Equation C would be the one that you'd want to use to do it in one step. Again, you can do it other ways, but that's the fastest way. Delta x equals VIT plus 1/2 AT squared. I have it up here now. And so now we're going to substitute into that formula, and it looks like this. Delta x equals negative 5.2 times 2.41 plus 1/2 times negative 9.8 times 2.41 squared. And again, from here, when you're solving, it's just the algebra. Negative 5.2 times 2.41 is negative 12.532. Half of negative 9.8 is negative 4.9. 2.41 squared is 5.8081. You don't have to show all the intermediate steps, but you do need to label your work as you're working it out so you can follow, or somebody else can follow what you're doing. From here, again, order of operations, you're going to want to multiply these together first before you add to this negative 12.532, and when you do that, you're going to get negative 40.99 meters as your displacement. Again, the rock's displacement will be negative because it has been displaced in a downward direction. It fell. Okay, now if I asked you the depth of the well, which is really what I'm asking, I don't actually want to put the negative in front of it when I'm giving it as a depth, or same thing with a height. I would just say it's 40.99 meters deep. Okay, but that is the displacement, negative 40.99 meters. Does anybody have a question about this particular problem? No? Okay, let's look at another one then. This time we're going to look at something with an initial velocity that is upward. We're going to throw something up in the air like a ball. It's going to rise up, it's going to fall back down. Okay? I know this picture makes it look like it's kind of being thrown forward. We're not dealing with forward. It's just, you can't draw it. It's just straight up and down. So imagine it's straight up and then back down again. And that's what it says. A ball is thrown upward at 3.4 meters per second from the ground. What will be the maximum height that it reaches? And so we have right now an initial velocity of 3.4 meters per second upward. I went ahead and labeled that as positive. So my initial velocity is positive 3.4 meters per second. And at first glance, that appears to be all that I know. But what else do I know about this ball? There you go. I know its acceleration because I know as soon as it leaves my hand, it's in free fall. Its acceleration is negative 9.8 meters per second squared. Again, your acceleration for any object, whether it's thrown up, down, or dropped from rest, is always this number. Okay, it's always negative 9.8 meters per second squared. Okay, I know I'm trying to figure out what its height will be up here, but I don't have enough information to do that yet, at least not on my screen. What else do I know about an object that I throw straight up in the air? Sorry? What can you tell me about this point up here at the top? That's as high as it gets, sure. What else do you know about its motion, though? It stops. Guys, if you throw something straight up in the air, it slows down, slows down, slows down, and for a split second, it stops because it has to turn around before it can fall back down again. It's not going to stop up there like, you know, a Wile E. Coyote in a Roadrunner cartoon, but it does stop. It has an instantaneous velocity of 0. For that instant, for a split second, it stops. And so I know at its maximum height, its velocity is 0. And I went ahead and called that VF. Because that's what I'm looking for, is what's happening at maximum height. That is the final position I want, because I'm trying to solve for its displacement up there. Okay, if you would rather label it instead of VF as V top, you can do that if that's easier for you. Okay, it doesn't really matter how you label it. You need to know, though, that this is the velocity at the top. Okay, and if you might want to add that to your notes as well, because you're going to see questions about objects thrown upward. The velocity, the vertical velocity of an object thrown straight up at the top is 0, okay, for all of them. So that's something that you can use as a piece of given information, and it's not going to be stated in the question, but it might be helpful for your calculation. So for an object thrown straight upward, its velocity at its max height or at its apex, whatever you want to call that highest point, will be 0. All right, so that's enough information now for me to solve for my unknown delta x. Because if I look at my equations, I can use one of these, A, B, C, or D, to solve for delta x when I know VI, A, and VF. Which equation can I use? Take a look if you're not sure. A, B, C, or D? B. Yeah, I can use equation B. I don't know the time, so I don't want to pick any equation that has time in it, and the only one that doesn't have time in it is equation B. And equation B happens to have VF, VI, A, and delta x. So that's the one we're going to use. Okay, so our equation will be this one. VF squared equals VI squared plus 2 times A times delta x. When I substitute in, it's going to look like this. 0 squared equals 3.4 squared plus 2 times negative 9.8 times delta x. Whenever I go to solve this, 3.4 squared is 11.56. And I did a couple of steps here, so let me explain what I did. I squared it, I got 11.56, and then I subtracted it over here. Okay, and that's why it looks like this down here. It becomes negative 11.56, because 0 minus 11.56 is negative 11.56, equals 2 times negative 9.8 is negative 19.6 times delta x. Okay, so I did not write all my steps here, and I probably should have, but hopefully you can follow along. Okay, again, I still need to isolate my variable delta x. I need it by itself, so I need to divide both sides now by negative 19.6. Negative 11.56 divided by negative 19.6 is 0.59 meters. It does make sense that this gave me a positive because my displacement will be upward from the ground, okay, and specifically upward by about 0.6 meters. So not very high. That wasn't going very fast. Okay, so my displacement, which is my maximum height, because we said we were looking for the point at which velocity was 0, which is maximum height, will be 0.59 meters. Questions about this one? Kind of trickier, so just checking. All right, here's a follow-up question for the same scenario. How long will this ball be in the air? Okay, I have the same information labeled. Here's VI, here's A, here's VF, here's delta x. This time I'm going to solve for time. Okay, if I want to solve for time, again, we look back at the same equations. I can use any of these equations that have time in them because I have every other piece of information that I might need. Okay, I have equations A, C, and D that I can use. In my opinion, A is the easiest to use of those, so that's the one I'm going to choose. But if you want to choose D, you could. Please don't choose C. If you choose equation C, you can solve it, but you will be using the quadratic equation. So if you really want to practice your quadratic equation skills, use equation C. Otherwise, don't. Okay. That, by the way, is something you need to keep an eye out on. If you have an initial velocity and you're trying to solve for time, don't use equation C. You will have to use the quadratic, okay? Because you're going to end up with something t squared plus something t plus something equals 0. Anyway, just a side note. So VF equals VI plus A times t. Let's substitute in. That gives us this. 0 equals 3.4 plus negative 9.8 times t. We're going to subtract that 3.4 from both sides. And then we're going to divide both sides by negative 9.8. Now, this is not your answer. This time is the time that it takes to get to this height of 0.59 meters. It's the time that it takes to get to this final velocity of 0. It's the time it takes to get to the top. It's the time up. Okay, it's not the total time. And this question didn't ask how long does it take to get to the top. It says how long is the ball in the air. So you might want to add this to your notes as well. Time up equals time down. It's symmetric. If it takes 0.347 seconds to go from the ground to the max height, then guess what? It takes 0.347 seconds for it to get back down again. So if you solve a problem like this where you're using the max height, then when you find time, you have only found half of the time. I have to double it. Please make some kind of note on your paper so you remember that later. If you solve for the time to max height, because you used a final velocity of 0, or because you used a displacement, in this case of 0.59 meters, you have to double the time. So the total time in the air is 0.694 seconds. It may say how long is the ball in the air. It may say what is the total time in the air. It may say what is the hang time. If you're not familiar with sports, you may not have heard the term hang time before. You might want to write that down in your notes too, but the hang time is going to be the total time in the air. Sometimes you'll hear them talk about hang time like on a punt in football, the hang time in the air, but that's the total time. So again, 0.694 seconds is that total hang time. Okay, questions about this one? No? All right, let's see if we can draw some graphs for it. Okay, what does the XT, VT, and AT graph look like? Well, on my position time graph, I need an object that starts going in a positive direction, upward, but slows down, stops, and then starts going in a negative direction while getting faster. It's going to look just like the trajectory would. Looks kind of like the shape you see in this picture right here. Okay, so you're going to get this for your XT graph. For your VT graph, your initial velocity is positive 3.4 meters per second. So you have to have a positive v-intercept, or y-intercept, y-axis, but v-intercept. You have to start up here, and it has to slow down, and then it has to stop momentarily, and then it's going to be moving down. So your graph looks like this, and it better be a straight line, because remember, the slope of your VT graph is your acceleration, and my acceleration is negative 9.8 meters per second squared the whole time. Okay, so it can't change slope. It needs to be negative 9.8 the whole time, so it needs to be a straight line. And again, that helps me with my AT graph. The slope of my VT graph is acceleration. This is a negative slope. Specifically, it's a slope of negative 9.8. I will say this, if we had graphs with numbers on them, sometimes 9.8 is hard to see, so you might see it on a test or quiz or worksheet as negative 10, just a heads up. Sometimes they round acceleration due to gravity to negative 10. Because it's easier to graph and it's easier to read. All right, but these are your graphs. And by the way, this AT graph will look like this, whether it's thrown upward, thrown downward, or dropped, because it's always that same value. Okay, those will look exactly the same for all of them. All right, this one says the velocity time graph shows data for a penny falling from the observation deck of the Empire State Building in New York City. How far has the coin fallen after 4 seconds? And I already gave you the answer because it corresponds to the area of this graph. You can find the area of that triangle. It will be negative 78.4 meters, and that would be how far it has fallen after that amount of time. Okay, again, if you have a VT graph, area is displacement, and it's always the area under your line, which under in this case means between the x-axis and those in that line. Okay, so this triangle here. All right, if the observation deck is 320 meters high, how long will it take the coin to hit the ground below? If you guys want to try this one on your own and see if you can get it, the answer you should get is 8.08 seconds, and you're welcome to try it on your own and make sure you get that same thing. This is slide 86, and so you are welcome to try that and even come back here if I leave it before you're done. And just make sure that you also get 8.08 seconds if you're trying to do some practice and check yourself. Okay, but I'm going to skip this or move on from this slide for now so that I can say this before I let you guys get to work, and I can put it back up in a second. You do have a quiz tomorrow. Okay, Unit 2 quiz is tomorrow. Unit 2 test is on Friday. For the rest of class period today, you were working on the assignment 202.3 mixed kinematic problem set, and this time you have to submit that Google Sheet because this is the 3rd tab. However, last week on Friday, I posted a new version of this assignment that was corrected so that it was giving you correct feedback. Please make sure, if you haven't done it already, that you transfer your answers over from the first 2 tabs. That way your score is accurate. Okay, because your score on the old one is not accurate. You're not going to want that to be in there. I don't even know if it's going to show up, right, because of the issues that we're having with it. So again, please transfer the first 2 over. They should be the same numbers. But this is the one you're working on today, 202.3 mixed kinematic problem set. You have the rest of the period to work on it. If you have questions, let me know. It is due by 11:59 p.m. tonight, so please make sure that you get it submitted before then.